recording. Can I get someone to give me a mic test 1 2 to make sure I'm recording you guys?
1 2.
All right, there we go. So let's get going. So first of all, main thing we want to understand, what the hell is flux? Like, give me your best interpretation of what flux is. Anyone want to hop in? Flux, question mark. What is it? So flux has something to do with the electric field lines, right? Something to do with electric fields. So if we have a surface, let's say we have a wall here, and we have some sort of electric field in the area, arbitrary, it's electric field going in some sort of direction in this area. Let's say this direction. How is the flux related to the electric field and this area A?
What was the question?
So what exactly is flux? Like, how is it related to like the electric field and like an arbitrary area? What exactly is flux? Like, just give me your best shot.
I'd say it has to do with how the like the arrows or the lines or the charge like interact with like different surfaces.
Something to do with the lines interacting with the surface.
Right.
Anyone else want to build off that? So the lines interact with the surface in some way. Does it maybe have to do with how many lines pass through the surface? Does that ring a bell for anyone?
Yeah.
Yeah. So the whole idea of what flux is, sort of like hand-waving flux, is basically, it's a way of defining how much electric field passes through a certain area. So in this case, however many electric field lines pass through our area A is the total flux, in a sense. And mathematically, does anyone know what that would be mathematically? How do we relate our electric field and our area to the flux?
Would that be the SI unit or?
So what would be the SI units of flux? Do you know what that would be?
Voltmeters.
Voltmeters. And so how would we define that in terms of electric field and area? So first of all, what's the SI units of electric field?
That would be Newton meters squared over coulombs.
Do you know what that would be in terms of volts?
Not sure.
The electric field in terms of volts is going to be volts per meter, I believe. So if we have something to do with relating our electric field E, which we know is volts per meter, and we also have some sort of relation with the area, right? And what's the SI units of area?
That would be meters squared.
Yep, meters squared. So we somehow have to multiply our electric field with our area, and the units check out, right? Because our meter squared cancels out with our meters to get volts meters, voltmeters, whatever it is. So is it just we multiply the electric field times the area? Is it that simple?
I think so.
Well, there is one specific example where that is the case, but it's not the general example. So if we have a surface here, say this is a cross section of the surface, something like that, and our electric field is perfectly perpendicular to the surface, and our electric field is constant, then the flux would be E times the area. But it's not always perfectly perpendicular, and the electric field isn't always perfectly constant. So does anyone know how we rectify that? How do we get what is the general form of flux? Should be here in your equation sheet. Given it right here, our electric flux, sigma E, we'll also see a magnetic flux later, so that'll be, or not sigma, it's phi, whatever it is, who cares? But we have our electric flux is equal to the surface integral, whatever that is, surface integral of E with the dot product of dA. So what exactly does that mean? We're essentially taking our electric field at every given point, whatever its value is, and we're going to essentially sort of slowly add up the dot product of the electric field with the area vector, which, does anyone know what is an area vector relative to an area? Like if this is our area right here, lying flat, what direction is our area vector going to be in? It's going to be to the left, to the right. Go ahead, Kevin.
Wait, would you say like lying flat?
Like, let's say, so we're looking at like a flat table surface. This is sort of like a cross section. We're looking at it sideways. I'm trying to sort of like imagine we have like a, you know what I mean? Like a flat surface. It's hard to visualize in 2D.
Right.
But so what direction is our area vector for this area going to face? Is it going to be to the left, to the right, up, down?
Perpendicular to it, so going up.
Yep, perpendicular. So either up or down, depending on how we want to, depending on how we define it. And usually, how do we define whether it's, for example, up or down for a given surface? Like for most examples you'll see in this class.
Away from the center?
Exactly. So if we have some sort of a, sort of symmetric surface, which is 99% of what you'll see in this class, you're going to have some sort of center, and positive means away from the center. So if this were one side of like a cube and the center is here, it's going to be upwards. So essentially we go ahead and we add up all those little dot products, and so that's where we get integrating from. We're going to integrate over the entire surface of the electric field dot product with the area. And that's how we get the flux. And now that seems a bit daunting, but trust me, any example you see in this class, the integral extremely simplifies down. So let's go ahead and hop into our first example. So we're going to have a point charge with a charge plus 4q. It's located at the origin, so let's say right there, plus 4q. And it's going to be surrounded by some invisible sphere with a radius r. First of all, I want to know what would be the electric field at the edge of the sphere. Just use Coulomb's law. And then what would be the total electric flux through the sphere? Let's take 5 minutes, then we'll go over it. If you have any questions, feel free to unmute and ask, or type in session text. Also, if there's anyone that has not signed in, you could do that real quick. That'd be greatly appreciated. Either check announcements or session text for the sign-in sheet. All right, so we have our point charge located here, 4Q, and it's surrounded by our sphere radius R. And the first thing I want to know is what's going to be our electric field at the edge of our sphere? So how do we calculate that? How would we use Coulomb's law to calculate the electric field?
You would use let's see.
Recommend look back at the formula sheet if you ever have any questions about anything.
Okay, so it'd be K times Q over R squared.
Yep, so it's going to be K times whatever our charge is, which is 4Q over R squared. And what direction is our electric field in?
It would be outward,
Yep.
positive.
Radially outward.
Radially
So we'll indicate that with an R hat. Essentially just means whatever direction we're in, it's in the direction, radially outward from the center. So at this point here, let's say right here, our electric field is outward. And for example, up here is directly upward, down here, it's like this, etc. So then how would we go ahead and calculate the total electric flux through our sphere? So let's go ahead and think. So we know our electric flux, the general form, flux is equal to the surface integral of E dot dA. We use little a because that's what he uses. So we have our electric field E dot product with dA. So there's a way we can significantly simplify this integral. And how would we do that? First of all, let's think about how do we get rid of this dot product?
Would the dot product just become that point on the sphere? So it would be, forgot.
So what is a dot product? So if we have, for example, A dot B, what does that equal to in terms of A and B and something else? Some sort of angle. So if we have a vector A and a vector B, A dot product with B is going to be, we have this angle here between them, theta. Be the magnitude of A times the magnitude of B times what? Does he actually give it on your formula sheet? He does not.
It would be
appears.
cosine theta.
Cosine theta. Yep. So A times B times the cosine of the angle between them. So what's the angle between our electric field vector and our area vector at any given point? Remember, what direction is our electric field in?
It's radially outward,
Exactly.
and
And-
so it would always be like the same as the surface.
Exactly.
Here.
Yeah, because remember we said before, our area vector is always outward from the center, and it's always perpendicular to the surface. So for a sphere, that's just radially outward, dA, at every given point. So that means the angle between E and dA is just 0. So what's the cosine of 0?
That's one.
Yep, exactly. So we can just get rid of the dot product. So it's just E times dA. Now there's one more thing we can do. How do we can pull one of these two out of the integral, right? Our electric field is constant at our surface, right?
Right.
So we can just go ahead and pull our electric field out, and then we have, and actually we don't have these vectors signs anymore because remember it's just the magnitudes. So E times the integral of dA. Now what's the integral of dA? And we're integrating over the entire sphere. Well, for example, the integral of dx is just x, right? So wouldn't the integral...
Oh, it would be A.
Yeah, the integral of dA is just the area. So E times the area, which, does anyone know what the area of a sphere is? What's the surface area of a sphere?
That would be 4 pi squared. Pi r squared.
Yep, exactly. And he actually gives it to you on your formula sheet. 4 pi r squared. So we were able to go ahead and calculate the electric field, which is a constant. And then we were able to use that to then calculate the total flux through our imaginary sphere, which if we then go ahead and plug things in, is going to be whatever, 16 k q pi, I believe 16 k q pi, right? K q 16 pi r squareds cancel out. Yep. So that's how we would go ahead and calculate the flux through our imaginary sphere. So now let's go ahead and change up the problem slightly. Instead of a point charge, we're going to instead imagine we have a sphere of charge. Let me actually make that a bit bigger and actually use that. Wow, amazing. So we have this sphere with a radius A, which is smaller than R. And we're going to have our same imaginary sphere around with radius R. R. So, first of all, what we want to know is what would be the volume charge density of our sphere of charge if it has the same total charge plus 4q? Let's go ahead and take 2 minutes and we'll talk about it. What would be the volume charge density? Okay, you might see it as the symbol rho. take one more minute, then we'll go over it. All right, so how do we go ahead and actually calculate a volume charge density if we're given, we know it's a sphere, we're given the radius of the sphere, and we know the total charge? How do we get our volume charge density rho?
Would you put the charge over the volume of the
Yep.
the sphere?
Exactly.
Not the smaller sphere.
Yep. So we know that our volume charge density is a charge per unit volume, so it makes sense that we just divide our total charge, which is plus 4q, divided by our volume of our sphere of charge. And so what would be the volume of our sphere of charge? What's the volume of a sphere?
That would be 4 over 3 pi a cubed.
Yep, exactly. So the volume of a sphere is 4/3 pi r cubed. In this case, our radius is a, and he gives that to you on your formula sheet. These are actually really useful. He didn't give these on the formula sheet in the past. I feel like a lot of people got hung up on that. So we divide by 4/3 pi a cubed. So we go ahead, 3 moves up to the top, the 4's cancel out. So it's 3q over pi a cubed. Boom. So that's our volume charge density. So now the other thing we want to know is, would our total flux through the outer sphere be different than from the point charge? So do you think it would be different, yes or no? And try to explain why. And we want to unmute and try to think about it.
I'd say yes, because, well, I was just looking at like the formula sheet, and there's like
You saying yes, you mean you think it would be different?
yes, it would be different because the radius would be greater.
So,
Yep.
But so it's the same radius here as our first problem, right? And here it's just a point charge. And here, instead of it being a point charge, it's the same amount of charge spread over a slightly larger area.
Okay, so it's the same R.
So it's the same R from the very center outward.
Okay, then it would be the same.
Exactly. It would be the same because it's the same total amount of charge inside. And, I mean, you'll sort of see with Gauss's law, where essentially the electric flux through a surface, through a symmetrical surface, is only dependent on, or the electric flux through any enclosed surface is only dependent on the charges inside the surface. Because the way you can think of it is any electric field lines coming out from this point are going to end up going outward, versus any electric field lines originating from outside the sphere are going to pass through one side and out the other. So net flux at 0. So our electric flux is going to be the exact same as the point charge because it's all enclosed and it's the same total charge. That sort of leads us into Gauss's law. So what exactly is Gauss's law? Does anyone understand and sort of want to give me their best explanation of what Gauss's law is? And how would we be able to use it to, for example, calculate our electric field here? Gauss's law is listed in your formula sheet, but it's not labeled as Gauss's law. So what here is Gauss's law?
It would be Q over E naught.
Q over E naught. So this right here,
I
right?
mean, yeah, the electric field equals, yeah.
Yeah.
Be the second
So
part.
Gauss's law is our electric flux, which we know from earlier, is our surface integral of E dot dA is equal to the total enclosed charge within our surface divided by epsilon naught, which is a constant. And value of the constant is like whatever 9 times 10 to the minus 12 or whatever it is. Oh, he actually gives it to you. Yep. 8.85 times 10 to the minus 12. So that's what Gauss's law is. And so we want to actually go ahead and how would we use it to calculate the electric field for this example here? We want to calculate our electric field for our, we have a imaginary sphere of radius r. We want to calculate the electric field at this distance r from the center of our spherical charge. Let's take 4 minutes, then we'll go over it. All right, so how do we go ahead and calculate our electric field out here using Gauss's law? So first thing is, what do we know about the electric field? Is it going to be uniform around this whole circle here, around this whole sphere?
Yes.
Yep. So our electric field is going to be uniform. It's going to be constant around this whole sphere because it's the same distance from every single point on our sphere of charge. So another thing, is our electric field going to be straight radially outward, from our center? Or is it going to be, slight, curving or turning or whatnot?
It'll be straight.
Yep, it's going to be straight radially outward. So it's going to look exactly like our electric field from our point charge. It's going to be constant around our entire surface, and it's going to be radially outward. So what does that mean about our flux calculation? Our electric flux, our integral of E dot dA.
Again, you can take the E out of the integral because the electric field is constant.
Yep.
Yeah.
Yep, exactly. The electric field's constant, so the E can come out of the integral, and the dot product. So the dot product. First of all, dot product. The angle is 0, so E times dA times cosine of 0. So it's E times dA. Then the E can come out. It just becomes E times the area of our sphere, and then our area of our sphere is, once again from earlier,
4/3.
That's the volume.
Oh wait, that's the
Has a 4 pi in it.
Yeah, 4 pi r squared.
R squared. Yep, exactly. So 4 pi r squared. And we know that has to equal Q enclosed over epsilon naught. So then, all we need to do is just divide our 4 pi r squared over, right? So then our electric field, E, is equal to Q enclosed over 4 pi epsilon naught r squared. And then we know it's going to be in the r hat direction. So is this the same thing as our point charge electric field? With this different constant, epsilon naught, and we have this 4 pi we need to deal with. How are K and epsilon naught related to one another?
Oh, K would like, since K is like 1/4 pi epsilon naught, it would just move pretty much the 4 pi epsilon naught to the top. And it would,
Yep, so K is equal to 1/4 pi epsilon naught. You have it in your formula sheet. So this is just K. So this is just K times our enclosed charge over r squared, r hat. Hey, that looks exactly like our point charge, right? Because we remember our enclosed charge, Q enclosed, is 4Q. It looks exactly like our point charge. So for our sphere of charge, even though it's not uniform, it's uniformly charged, but essentially we can treat it as if it's just a point charge at the center, and it has the exact same electric field, as long as you're outside the charge. As long as R is greater than A, then the electric field looks exactly as if it would from a point charge. Super easy, right? So if you have a symmetrical situation, you can treat it as if it's just a point charge. So let's go ahead and hop into another example here. Does anyone have any questions about this before we move on? Feb 1. All right. Let's go ahead and open a new one. So we're going to go ahead and take a look at a uniform line of charge, an infinite line of charge. So we're not talking about a point charge or a sphere of charge. So now we're going to have a uniform line of charge, and it's going to be very long. we're going to treat it as if it's infinite and going off in each direction. Oh, this is going to annoy me. Come on. Perfectly straight. There we go. So we have our uniform line of charge with charge density minus 3 lambda. And we want to go ahead and calculate our electric field, a distance r, let's say right here. Your distance r from our infinite line of charge. We want to go ahead and use Gauss's law to calculate this. So let's go ahead, let's say 10 minutes, and then we'll go over this. If you have any questions, feel free to ask. All right, so we have our infinite line of charge. We're given its charge density. And we want to go ahead and use Gauss's law to calculate the electric field, distance r from the y-axis. So first of all, we want to know, how would we first appreciate this? So how would we first approach this? How do we draw our Gaussian surface that we're going to use to calculate?
You'd use a cylinder.
Yep, exactly. So we're going to draw a cylinder. Let me actually go ahead and... Is there a way I can only expand that way. All right, let me go ahead and do this. So I just have a little more room to work with. Okay, just move ahead. There we go. So we're going to go ahead and draw a cylinder. So what is our cylinder going to look like relative to our line of charge? It's good.
The point will be on the surface of the round side of the cylinder.
What was that?
It'll be like on the surface of the side surface of the cylinder.
So like the line of charge is going to be straight up the middle?
It'll be straight out the middle, yeah.
Yep, exactly. So we're going to have our Gaussian surface, our cylinder. Let me go ahead and draw it. So we want our cylinder to be parallel to the line of charge, so that the line of charge goes straight through the center of our cylinder. And so we have our 3 parts of our cylinder. We have the top, we have the bottom, so we'll call it, so we have the side where it wraps around, part 1, and then we have the top as part 2, and the bottom is part 3. So we have 3 parts of our cylinder. So now let's go ahead and take a look at Gauss's law. So remember, what's Gauss's law again? Let's just write it down. And let's say our cylinder has a length L from top to bottom. So what's Gauss's law?
Wait, would we be using never mind. I think.
Wait, no, go ahead. What are you thinking?
Well, I was just looking at the formula sheet, like in the table, but that's just the magnitude, like the row that I was looking at, the 3rd, 4th row. But
What you mean the
magnitude of the
2k lambda over r?
Yeah.
So that's what we're going to be deriving here. So that's our final answer. So that's the sort of idea of where we want to get to. But we want to understand how we actually get there using Gauss's law.
Right.
So once again, Gauss's law, go ahead and write it down. Our flux is our closed surface integral of E dot dA over our entire surface. That's what the little circle thing, the closed surface integral, E dot dA, which is equal to our total enclosed charge over epsilon naught. So that's the first thing we want to look at, is what is our total enclosed charge within our Gaussian surface? What is the total charge within it?
Minus 3 lambda.
Well, that's the charge density, charge per unit length.
Okay.
And how long is our line of charge?
Infinite.
Infinite. So it's an infinite amount of charge, right? How much of it is actually within our Gaussian surface that we've drawn?
That would be -3L.
Yep, -3 lambda L. So,
Lambda L.
so Q enclosed is equal to our charge density, charge per unit length, -3 lambda, times our total length, which we're saying is some arbitrary value L. So now, we know we have our -3 lambda L over epsilon naught. And that's what we know our flux is going to end up being. So now we want to figure out what this closed surface integral is so we can actually solve for our electric field. So let's go ahead and break our integral into 3 parts. We'll say part 1, which is our integral of E dot dA1, which is around this entire encapsulate the part that's surrounding the line of charge, the part of the cylinder that's not the 2 end caps, plus our E dot dA2, which is for the top, plus our integral of E dot dA3 for the bottom. So which one of these, if any, can we go ahead and instantly say is 0? And why?
Two and three, because the area vectors for those are perpendicular to the E.
Exactly.
The electric field.
Yep. So what direction is our electric field? From the line, what direction is our electric field?
Out radially.
Yep. So our electric field's always going to be going outward. So straight left or straight right in the sense we're looking at it. Or also into or out of the page, if we're thinking about 3D. So our electric field is always straight left or right. And our area vector for the top is in what direction? dA2, up, exactly. And dA3 is?
Down.
Down, exactly. Either way, the angle between E and dA is 90 degrees. Dot product E dot dA, E times dA times the cosine of 90 is equal to 0. So both of those go away. So we only have to worry about the parts of the cylinder, the side part of the cylinder, the actual height of it. And so what is our angle between our area vector dA1 and our electric field? Our area vector dA1 is going to be radially outward, right? Because it's always perpendicular to the surface. So what's the angle between that and our electric field? Zero, exactly. Cosine of 0 is 1, so it's E times dA. And since we know, because it's symmetrical, then our electric field is going to be constant. So then our electric field magnitude can come out of the integral. And we have the integral of dA1. E times the integral dA1. So what is our total area of the side of our cylinder?
In this case, it would be the height of it, or the L, multiplied by the circumference.
And what's the circumference?
2 pi r.
2 pi r, exactly. It's just the circumference of a circle with the radius r. So E times L times 2 pi r. So now we have everything we need, right? We have our enclosed charge, which is negative 3 lambda L, and we have our E times, it's our integral of E dot dA. So if we go ahead, plug things in, we know that has to equal negative 3 lambda L over epsilon naught. So we go ahead and bring it down here. Our L's end up canceling, and we can solve for E. The 2 pi r comes down here. So we have negative 3 lambda over 2 pi r epsilon naught. And we know it's going to be radially outward in the r hat direction. Is that what's here in the equation sheet? Because in the equation sheet, I remember Kevin mentioned earlier, we had this E of r is equal to 2k lambda over r. Is that the same thing that we have here? I want to double check we actually got the right answer. First of all, how are k and epsilon not related?
Sorry, I'm a little slow on the math. So it would be the same scenario, I think, with let's see, taking out the 2 pi r epsilon, or 4 pi r epsilon, and then leaving behind.
So k is equal to 1 over 4 pi epsilon naught, right? So then we'll leave our negative 3 lambda up here, since that is what our lambda would be. So, and then we know that, so we'll have our negative 3 lambda, we're not going to touch that. And then we have 1 over 2 pi epsilon naught, which, wouldn't that just be 2k? So we have 2k over r. So we have 2k times our charge density, lambda, which in this case is negative 3 lambda, because I like to be annoying. And that's the sort of stuff you'll see on Flip It. So 2k lambda over r hat. It's the same thing. So with Gauss's law, we're able to derive our electric field, a distance r from our infinite line of charge, and we find that it does indeed match up with what we are given in our formula sheet. Boom, magic. Does anyone have any questions about this? Anyone a little lost or confused? All right.
Pretty much got it.
Yeah.
A lot of this was taking apart, the scary integral, and in a lot of cases, the electric field would be constant.
Exactly.
Often be like the case in a lot of the integrals.
Yeah, exactly.
And
yeah.
Then as far as the not surface area, I keep thinking it. The dot product, the dA. There you go. I'll just say that. You would see if it was aligned with the direction of the electric field, which in often cases it does. But if it doesn't, it's the two magnitudes, the absolute value of the two magnitudes times cosine theta. So you would just figure out, the one of the components that would be like perpendicular.
Exactly.
And then you keep solving from there, pretty much.
Mm-hmm. Yep, so the whole idea here that we want to see that this integral looks scary, but every single example you'll see in this class, all the components of the integral are always going to be E and dA are going to be either parallel to one another, which means it's just E times dA, and then E can come out of the integral because E is pretty much always going to be constant with what you see in this class. Or they're going to be perpendicular, which means cosine of 90 is 0, so they go away. So that's literally what it is, and that's Gauss's law. Gauss's law significantly simplifies some of these really annoying problems. I mean, because what else we could do here is we could go ahead and, if we select a point, we select our point R, and we could integrate over this entire line of charge from negative infinity to infinity. And we could go ahead and try to derive the electric field like that, but it just gets ugly. And it's not fun. And you have to make certain assumptions before you go in. And it's not fun. Gauss's law turns what's normally about a 10-liner integral that, honestly, I don't expect any of you guys to have the patience to be able to go through, into a literal 3-liner, break the integral down. Oh, 2 parts go to 0. Solve for the electric field. Boom, easy. So, because Kevin just said, to sort of summarize Gauss's law, what is it? It's flux is equal to E dot dA, which is equal to Q enclosed over epsilon naught. For what kind of surfaces? What has to be the case?
Symmetrical?
Yes. So we have to have some sort of symmetry. So Gauss's law is E dot dA is equal to Q enclosed over epsilon naught for symmetry. And what are our 3 kinds of symmetry we'll see in this class?
It would be, I'm not sure if it's the right term, like radial symmetry?
So like spherical?
Circles and whatnot? Yeah, spherical.
Yep, so we have spherical. So spherical symmetry, like we saw in the first example. And then what's our second type?
Would it be linear, or I guess that wouldn't be the term.
What kind of symmetry is this? This example right here. Is that what you mean by linear?
Yeah, that's what I meant.
Does anyone know what?
Horizontal and vertical.
Not quite. I'm thinking what shape is our Gaussian surface here?
Cylinder.
Yeah, cylindrical. That's the term I'm going for. Yeah.
Oh, okay.
But yeah, I mean, you guys know what it means. You guys understand it. Cylindrical. And there's one more type of symmetry that you guys will see. And I'll likely have an example on it tomorrow.
I guess it'd just be planar going off.
Yep, exactly, planar. So, so if we have a plane, let's say this is a side view of it, it goes into and out of the page. Then we can go ahead and draw a Gaussian surface that is symmetrical on both sides of the plane, and we can calculate electric fields like that. All right, cool. So, does anyone have any last questions about this?
I guess one thing I noticed on the formula sheet is cylindrical cell. I just thought it was it included the other 2 surfaces, the top and bottom. I mean, it would be in helpful math expressions, on the
So what do you mean?
side.
It would be down here on the bottom?
Not at the bottom. It would be on the right-hand side. Right.
Oh, yeah.
Cylindrical shell would just be that round surface, not the circles included.
Yeah. So
that's what I assumed it would be. It would be like the surface area of the entire thing.
Yeah.
So yeah, before I was trying to take out the circles or something like that, by taking out pi r squared or something. But it was already done.
Yeah, exactly. So the surface area of an actual 3-dimensional cylinder would be 2 pi RL plus 2 pi r squared, because 2 times our areas of our circles, which is pi r squared. In this case, he's only giving you the 2 pi RL because you don't have to worry about those end caps.
All right.
Yep. Significantly, nice and easy simplifying. So, but yeah, so we have our three types of symmetry: spherical, cylindrical, and planar. And we can go ahead and calculate our electric fields by, use Gauss's law. We can find our enclosed charge. So multiply whatever our charge density is by the total length or volume or area, whatever it is, enclosed. And then we go ahead and just solve E dot dA, figure out which parts go away and which parts are just E times dA, which is just E times A. And then we just divide by the area, divide Q enclosed over epsilon naught, and divide that by the area to get our electric field. Boom, magic. It's a bit annoying to get the grasp of conceptually of what's going on, but trust me, it makes your lives so freaking easy, especially if you go into higher level physics classes. But I know 99% of the people that take this class are mechies or chemies, and then comp sci. For some reason, there's a lot of comp sci people that take physics.
No idea why. I'm one of them. No idea.
I mean, I suppose like
Biochem.
Oh yeah, biochem.
All of a sudden, like, I'm looking at spheres and freaking all of this. But,
Yeah, we've got the one random senior biochem major in here. Like, what the hell are you doing, Ben? All right. Well, that's basically it. That's Gauss's law. Hope this helped out a bit. If you missed part of the session, I'll go ahead and upload it and post it in the Session VODs channel later on. And we'll have some more practice problems with Gauss's law. And I'll specifically have at least one example with the planar symmetry tomorrow, but also more practice with some spherical and cylindrical symmetry. Same time tomorrow, 1 o'clock. Thanks, guys, for coming. Hope you guys have a good day.
Thanks, man.
No problem.